So here we go. The record is on. Let us recap what we did last week. Okay. Now, last week we were talking about the fact that we could write moment in one element or one member like this into three terms. The first is the moment due to the load alone. So when I say the moment due to the load alone, it means that we do not take rotation or joint deformation into the account. It's just moment due to the load. So that's how we can create a formula for any kind of load to give us the fixed end moment. The second one is moment due to rotation. Now, after the derive of this, we now have the relationship between the moment that is caused by rotation. You can see the relationship of the moment at one end will depend on the rotation at both ends. Okay, and thirdly, we also developed the moment that will be induced by the joint displacement. So we got this. So now when I say we can write moment in three groups, I should say that we can also combine them in the end, right? So we are going to do just that. So now we can write Mij by add everything up. Okay, so you're going to have 2EI over L coming from this one, you see, 2EI over L, 2 zeta ij plus zeta ji minus this 6 EI delta. I should say delta ij or ji just the same, right? Okay. Over L square plus FEM ij. Now we can do some rearrange, and by saying that if I measure this rotation, look carefully, okay? If I draw the line from this to connect with that, this angle is psi angle. Okay, so this is not the joint rotation. It's not zeta ij. It is psi ij, and this psi is equal to delta. Oh, it's at j, so I should write delta ji. Maybe I should also change this to ji. I'm sorry. Be consistent. Delta, so the psi is delta ji over the length of the member. When I plug this back in here and rearrange the term, now I can write this as Mij is going to be equal to 2EI over L, 2 zeta ij plus zeta ji minus 3 EI can come out, and because there's 6, so we got 3 left, and L can come out. So now zeta, we have zeta or delta over L inside, so it becomes psi ij plus FEM ij. And similarly, your MJI is in the same fashion. It's going to be 2EI over L, 2 zeta ji instead of ij, plus zeta ij minus 3 psi ij plus FEM ji. Okay, Notice that now we have the relationship between moment and joint rotation, joint displacement, and moment due to the load. Notice one more thing, that this is the stiffness of the structure, right? It is the thing that change rotation into moment, change the joint displacement into moment. So that is a stiffness. And when we are talking about the indeterminate structure, that means it is always going to be involved with stiffness. All right. So that is our slope deflection equation. Forgive me 1 second. Oh, I forgot to I was worried about one thing, so I need to go check quickly. Okay, so we are back here. Now we have the slope deflection equation. Okay, so no more to it. It's time to look at the example. Okay, now I kind of demonstrated this last time, but since they are here, let's do the quick recount of the problem with the force method. Okay, now that you know how many unknowns we're going to have here. 1, 2, 3, 4, 5, and 6, right? So if we consider force method, we can neglect the horizontal force, right? So we have 6 unknowns and we have 3 equilibrium equations. So that means we are, not 3, because we already discount for the sigma fx equal to 0. So that means this is 4 degrees of redundancy. Okay, so if you are going to solve this with the force method, you probably have to create the primary structure out of this. It looks like that. So if I can call this A, B, C, and D, you are going to solve for zeta A, delta B, delta C, and zeta D. So not a good thing to do, right? I'm not going to go into details because we are not doing the force method anymore. Just try to complete the example that you have. I think what I have forgotten to do is that I forgot to post the links for the video that I did last year. So I think I'll do that. I think I will turn the option from unlisted to public. That's easier, so you guys can watch some other things as well. And this is another one that I did last time, right? This has 1, 2, 3, 4, 5, and 6 reaction if you count for horizontal force. So this is 3 degrees of redundancy. So your primary structure is going to look like that. Maybe if you choose to remove all the reactions in the middle, that's my preference. It's just going to come down like this, and you have to solve for delta B, delta C, and then delta D, and so on. Okay, this is not a viable thing to do anymore. But that is why we are going to start doing the slope deflection. Okay, so now let us try to get a good start out of this. What I used to give you in the exam is something like this, but because it is extremely highly likely that we will have the online exam, so I can't give something like this anymore. So let us try to see what's going on here. I want you to try to do it yourself. So, okay, look at this. Write the problem statement for the structure shown if the method of slope deflection is going to be employed. Okay, so first you need to know how many degrees of freedom of this structure. In fact, how many, rotation or joint displacement you have to solve. We talked about this last time, right? So it is a good idea for you to be able to write the statement. But you know what happened? When I tried the first few times, most of the students here are pretty good. If you were asked to solve the problems, you can do it. Most of you can do it. I could say all if you can cut out the mistakes. But when I ask you to try to summarize what you need to do without doing it, many cannot do it. You have to solve the problems first to see what you need to solve. So that most of people are like that. Many are like that. You don't see the destination until you start your journey. So it's kind of weird. So when you actually try to solve the problem, when you go out in the real world and try to do the real work, you should have the destination in sight, at least you should be able to expect what are you going to have. So many cannot do this. If I ask you how many unknowns you need to solve, some would just, oh, I don't know, I need to just solve it. And then I'll know how many unknowns we need to solve. Do you think that is a right thing to happen? How can you not know the unknowns and you solve them and then in the end you can solve the structure? But if I ask how many unknowns you need to solve, you can't answer it. So how many degrees of freedom does this beam have? Remember the last time? It was only last week, How many degrees of freedom? I'll give you 30 seconds, okay? Or 1 minute. Waiting, okay? Try to figure it out yourself. Both beams, we have 2 beams. How many degrees of freedom do you need to solve? All right, I'll give you 1 minute to think about it, okay? Anyone? Wow. Anyone? Oh, it's a problem. That's the answer in the chat. 2 and 5 from your senior Nutipong. Thank you very much. So do you agree? The first one has 2 degrees of freedom. Do you agree? All quiet. Excellent. So here's the rotation. That's another rotation. Remember your slope deflection equation. It has rotation, joint displacement, and moment due to the load. So we are solving for rotation and joint displacement. And this beam, you don't have to have any joint displacement. So you have 2 rotation here. So you can say this is the beam with 2 degrees of freedom. You should be able to write this statement before you do anything. And if I give it a name, like A, B, C, and D, now you should know that your degree of freedom, delta B, zeta B and zeta C. And the second one, you have rotation here, 1, 2, 3, 4, and 5. So it's 5 degrees of freedom. Okay. And if I give name in the same fashion, A, B, C, D, and E, your unknowns are zeta A through zeta E. Now, let's say, I don't know if you have had any class that has taught you about symmetry, but these two beams, they are symmetric, right? Do you agree?
Yes, yes.
They are symmetric structure. So what can you tell about the symmetric structure? Why are they symmetric? Why are they symmetric?
The loads and the distance.
Huh?
Load and distance is equally in both parts.
So the distances are equal in, say, all parts, both parts, some parts. So I think the most, say, basic definition of the symmetry is that you have the line of symmetry somewhere, right? So you would agree that the line of symmetry is here in the middle. Do you agree?
Yes, yes.
And when you fold them, they become the same picture. That's symmetry. When you fold them about the axis of symmetry, they become the same picture, right? Or they fall on top of each other completely. And right here, this is the line of symmetry. So when you fold them, if you fold E onto A, everything looks exactly the same. Am I correct?
Yes, yes.
This is the line of symmetry. Which means whatever happens at A will be exactly at whatever happens at D in the first beam, right? So whatever happens at B will be exactly the same as whatever happens at C. That's symmetry, right? We're talking about the first beam. Come on, guys, even kids know it. So let's say when I draw the deflected shape of the beam, this is fixed end, so it's zero rotation, right? This line supposedly should be exactly the same and opposite to this one. Am I right?
Yes, yes.
Say if I have the deflected, it should be like this. Because if the beam is symmetric, my deflected shape should also be symmetric, correct?
Yes, yes, yes.
Good. Just only you and me, right, in this class, right?
Agree,ครับ.
Okay, okay, okay. So just look at rotation at B and C. According to my sketch here, rotation at B is clockwise or counterclockwise. Rotation at B is counterclockwise or clockwise. Can anyone say anything? It's counterclockwise. And rotation at C is
Clockwise.
But they are symmetric. So that means, can I say theta B is equal to theta C? Is this correct or not?
We need to have minus sign.
Excellent. We need to have minus sign somewhere because the magnitude is the same, but not the direction. So if you have a symmetric structure, this is another information that you can gain from. So that means degree of freedom of the structure when taking advantage of symmetry. So with symmetry, How many degree of freedom do you need to solve?
Only one.
Only one. See, one unknown. And you can solve this beam very easily. Now, this is exactly the same beam as we have here. You see, it's exactly the same as this one. If it's the force method, you will have 4 degrees of redundancy. So you have to establish 4 compatibility equations. That means you have to calculate numerous deformation, which is completely unacceptable if you have a race against time or something like that. So let's look at another one here. Now that you know, this beam is also symmetric. So if I say we take advantage of symmetry, what do you know? What can you tell?
3 degrees of freedom.
3, that is quick. Very, very good. So I meant to you to do this first, but it's great. It is 3 because you can say theta B will be equal to, is it going to be the same or is it going to be different? Let me try to draw. Okay, this one is counterclockwise, that one is clockwise. So it is this, right? And then theta A is equal to minus theta E, right? So with symmetry, you are down to 3 degrees of freedom. So many times we are going to build the structure that is symmetric, because you can see that we're going to design or construct a continuous beam where you have equal span length and pretty much the same uniform load acting on them. So when you run into a situation like this, you should be able to solve them very easily in a few minutes. Okay, so any question on this? All right, so let's move on. Now, okay, we are going to solve the first continuous beam. So it's that beam again, but I don't know if I meant to leave the load out for you guys who have it, but because the fixed end formula is WL squared over 12. So I'd suggest that the W is equal to 1200 kilogram per meter to ease off our calculation. Unless, of course, you like another name. Well, see, I expected that it's going to be complete silence again. But before we do this, let me show you something. Handout, okay? The good thing about this, why do we have this? Okay, this is a slope deflection method, okay? And this is the equation itself, which we already finished. Now, there is a procedure that you can follow. So that is, in a way, makes this class a little bit easier than CVE337, because that one requires complete understanding. So you can start off by process number 0. Of course, you need to know degree of freedom that you need to solve, which we just mentioned. The second one, we will define the stiffness of the structure relatively. You can calculate your fixed end moment and you write your slope deflection equation. And then once you know the slope deflection equation, how are you going to solve it? You're going to put them into equilibrium. Okay. And then that's it. Okay. That's it. We have these 5 steps to, ease the difficulty of using the method. So without further ado, you have to keep your 5 steps in mind, and we are going to start doing this. Okay. So we already determined this. that we have 2 degrees of freedom. If you are brave, you can say, hey, I know that this is going to happen, so I can solve this with 1 degree of freedom. So I'm going to try to give the full account so that you can see the picture, and then I'm going to try to reduce this for you so that you can see as well how your ability to take advantage of the situation can help reduce your work. Okay, so in the beginning we can say that step number 0, this guy has 2 degrees of freedom, because this is when things got messed up. Because what is theta A? This is fixed support, remember? Let's call this A, B, C, and D. Theta A is, anyone?
0.
0. Theta A is 0. But still some folks, you know, when they count degree of freedom, they say 4. But then when they start writing the equation, they say theta A is 0. So I cannot say they are really wrong, right? I cannot say that they are really wrong. But how can you say 4 when you know theta A is 0? You know it's 0 already. So you don't need to solve them, right? But then when they write the equations, they say theta A is 0. But when they count degree of freedom, they can't. So that's exactly what I said. Many of you would have to start doing the problems before you know what the problems are. You know, it's not a very good thing to do, if you ask me, but it doesn't really, you know, kind of say destroy you in a way. But if you know you're gonna say theta A 0, why count it? It shows that you don't have a clear understanding of the problem that you are handling. Not a good sign. So 2 degrees of freedom, because theta A is 0 and theta D is also 0 because they are fixed support. Okay, the next one, step number 1, is the relative stiffness. Now, when we go back and look at the slope deflection equation, as I mentioned, this is the green thing, this is the stiffness. Okay, so 2 is constant, E is the material property. Therefore, when we talk about the stiffness of the member, it's I over L. The larger the I, your structure becomes more stiff. The longer the L, the less stiff your structure becomes, right? If it's long, it's very easy to deform, so it's less stiff. And with greater I, you know, it becomes harder to deform, so it's more stiff. Simple as that. So this funny thing is, this is the one that always kills students. But in this case, the stiffness of member AB, when we talk about stiffness, we can always use K. The KAB, it is I over 6. All right? And KBC is also I over 6. And KCD likewise is I over 6. So relative stiffness means that now we know every member has the same stiffness. So I can say KAB is equal to K. KBC should be equal to K as well. KCD is equal to K when I say K is equal to I over 6. Now this is, you know, the management of the least common number, or coronal in Thai, right? So it's the least common number. And sadly, some students cannot do this. So you don't have to do this, the relative stiffness, but if you can, it will help you see, you know, how each member is stronger than each, you know, in comparison. So step number 2 now is the fixed end moment, the calculation of fixed end moment. Now, the fixed end moment is the moment caused by the external load, right? So its direction is always trying to counter the load like that. And I have said sometime before that in the universal way, the slope deflection it doesn't mean that you have to do it, but most engineers in the world would use it like this. We take rotation as clockwise positive. So that means if I calculate fixed end moment at A, now instead of, not instead of, sorry. So FEMAB, look at the direction, it is counterclockwise. So this is minus WL square over 12. This formula can be taken from the table. Okay, no excitement. Where does it come from? It just because it is the formula to calculate the moment due to the load alone. So it has nothing to do with support conditions or anything. It's just the function of the load. So you can easily calculate that. Okay. So this becomes minus 1200 6 square. Be careful of the square and then this kind of thing, you know. So that's 3600 minus 3600 kilogram meter. Okay, and likewise FEMBA this time. FEMBA, you can see now that it is clockwise, so it becomes positive. WL square over 12. So that is 1200 positive multiplied by 6 square over 12. And you know, you have to say that the calculation of fixed end moment will reflect on the load that your structure have on it. So the failure to calculate fixed end moment, which is very relatively easy, will mean that you are analyzing the structure with not the same loading condition. I have to say that. So if you get the fixed end moment wrong, the rest will become garbage. So please be mindful and concentrate and focus very, very well when you calculate this, because many silly mistakes occur here. Like instead of using 12, it becomes a WL square over 8 or something like that. Or it's 12 and you write 12, but then the next line becomes like 2 or, you know, whatever. Be very, very careful here. Okay, so it's 3600 kilogram meter. All right, and you should know that FEM, I should write down, maybe I should, FEM BC again is equal to FEM CD. It is equal to FEM AB, which we already calculated. That is minus 3600. Okay, and then we have FEM CB should be equal to FEM DC, which is already equal to FEM BA that we just calculated. So that is 3600. Okay, so the second step is done. So the third step is the slope deflection equation itself. Number 3, SD equation. Okay, are you excited? The first one, MAB. You can try to open the split screen window somewhere to see Maybe this one, it's a formula, okay, right there. So we have 2EI over L, but when I consider the relative stiffness here, the I over L becomes my K, right? So my equation can be rewritten as 2EK. So right here, because I over L is I over 6 and they're all equal, and I use relative stiffness, so it becomes K. So now I can write my MAB is 2EK. According to the formula, 2 zeta A plus zeta B. You know, in the development, to be, you know, maybe more universal, so to speak. So I call zeta IJ, but in fact, you can call zeta A. It's much more convenient. Okay, minus 3 psi of member AB, and then plus fixed end moment of AB. Okay, so now we know that zeta A is equal to 0, and psi is the angle of the member, the entire member, when you have joint displacement. And we don't have any joint displacement, so that is also gone. So now MAB is basically 2EK zeta B, and FEMAB, that's minus 3600. So that is my MAB. So you can see, if you know what zeta B is, you can easily obtain MAB, right? And we can proceed to MBA now. Again, 2EK. MBA is on member AB, okay? But it's on the another end. So you now have 2 zeta B plus zeta A minus 3 psi AB plus FEMBA. And again, zeta A becomes 0, and the psi term is also 0 because we don't have any joint displacement. So this becomes 4EK zeta B plus 3600. Okay. I think you guys should be okay by now, so I'm not going to stop and ask you if you have any question. But if you do, don't hesitate. Now we move on to the second member, MBC now. The K is the same, so it's 2EK, 2 zeta B plus zeta C now, and then minus 3 psi AB plus FEMBC. Okay. Now, because neither of them is 0 except the psi term, so here we have 4EK zeta B plus 2EK zeta C minus 3600. Okay. Notice that if you can take advantage of symmetry, your work probably ends here. But let me show you the full process. So MCB is up next. 2EK, 2 zeta C plus zeta B minus 3 psi. Oops, that's not AB, right? Apologies. That's BC. Plus FEMCB. So that is also 0. Now you have, now it would be a good idea because I'd like to try to keep, you know, the unknowns in the same vertical line, so that when I write my equilibrium equation, things become easier and I will be less susceptible to making mistakes. So I'm going to swap here, and now I'll begin with 2ek theta b, okay, plus 4ek theta c plus 3600. Okay, if you do not wish to use symmetry, you're going to have to write CD, which is going to be equal to the same. It's like 2ek 2 theta c plus theta d minus psi cd plus FEMCD. But you know theta d is 0 and psi is 0. So this becomes, again, I try to keep them to the same line for ease of the calculation in the future. So I'm just going to put the 4ek theta c here, so that you see the c here, and then c there. That one look like c. Well, let's do it again. 4ek theta c. And this one is minus 3600. Right? And then MDC now is 2ek 2 theta d plus theta c minus, oops, got the 3 psi cd plus FEMDC. And again, we know that this is 0 and that is 0. So MDC, to keep it with same arrangement, now I have 2ek theta c here plus 3600. So that's it, our slope deflection equation. Okay, what next? I suppose next is the break, right? Because it's 10:20. Do you want me to finish the equilibrium equation first before the break, or you will come back after?
Let's finish it now.
Oh, great. You're always in high spirit. So, okay, now you go back to the unknowns. Let's see, if you identify that you have 2 degrees of freedom, that means you are solving 2 unknowns, right? So that means you need 2 equations. So we're going to write 2 equations. And now we have the equations of the moment at each joint. What do we know if we are going to establish the equilibrium equations? So that would be our step number 4, right? We try to, okay. Step number 4, equilibrium equations. What do you know about equilibrium in this beam? What do you know about equilibrium in this beam? Moment, equilibrium moment. What do you know? Do you know moment at A? Do you know moment at A? Kind of silent. No, you don't. There'll be some value because it's a fixed support. So there'll be moment at A. There'll be magnitude. So we don't know anything. But moment at B, to maintain equilibrium, moment at B, the summation must be 0. And likewise at C. So your equilibrium equations will be sigma MB, which is equal to MBA plus MBC must be equal to 0. And likewise, sigma MC, just going to be MCB plus MCD. They must be equal to 0. So you now have two equilibrium equations to solve for two unknowns. So let's do it. Now you see the reason why I try to write my slope deflection equations that way. So when we try to establish this, MBA plus MBC equal to 0. So I just add these two equations together. So now I have 4 and 2 here, and you see that one is out the window. So sigma MB equal to 0. I have 8 EK theta B plus 2 EK theta C equal to 0. Next, I have sigma. It doesn't look like sigma at all. Sigma MC equal to 0. Now that means I am combining these two then. See? So it's 2 EK theta B plus 8 EK theta C, and then this one cancel out again. So now we have 2 EK theta B plus 8 EK theta C equal to 0. So that becomes equation number 1. That becomes equation number 2. So for those of you who do not wish or do not know how to take advantage of symmetry, you will end up having two equations to solve. But for those of you who know how to take advantage of the symmetry, your theta C will be gone from your process since here, right? This is your theta C, which you know is going to be equal to how much? Theta B is equal to minus theta C if symmetry is considered. So that reduces your work dramatically, right? Some would say, okay, I can take the advantage here. Here. Theta C is equal to minus theta B or vice versa. So it's gone. So what do we have here? In order for this equation to be true, now you must have EK theta B equal to I'm sorry, EK theta C equal to 0. Wow. The rotation will have to be 0 because it's symmetric. Right? So now, because we have passed the time a little bit, now we have solved the unknowns. We will come back and finish this problem in the next hour. Is that okay? It's going to take a few more minutes, and I think I can point out a few points. It's bad grammar. I can point out a few more things as well. So let's stop the record here.